Okay, everyone, after that introduction, we're going to talk about derivatives and graphing and how they all relate to roller coasters. So as we get into this, you're going to see we're going to talk about when you have a function that's increasing and decreasing, so like a roller coaster. Wherever a function is increasing, the tangent lines, the slope of the tangent lines would be positive. And so you can see in this case, the tangent lines have a positive slope. That means the first derivative is positive in those regions. Now, in the next section, where they're decreasing, so where they're going downhill, that would mean that the tangent line has a negative slope. In that case, since tangent lines have a negative slope in that region, we would say that the first derivative is negative. Now, where the function changes from either increasing to decreasing, so in this case, where you're going up and then suddenly you're going down, or where you're going from decreasing to increasing, so you were going down and now you're going up, we say that in that region, functions may have local maximums or minimums. And in order for those to occur, the first derivative must be 0 at that point because the tangent lines must be horizontal and they must have a slope of 0. It is also possible that the first derivative might not exist at those points because we've seen that before, where you have spikes or peaks, and the first derivative doesn't exist on spikes and peaks, but you can still get local maximums and local minimums at those spots. So you have to pay attention to wherever it doesn't exist as well. Now, as we move on into the next little section here, here's an example problem. Identify the open intervals on which the function is either increasing or decreasing. So we would take a look at this function and we would ask ourselves, where is it increasing? So it's going up in this region and it's also going up in this region. So it's increasing from negative infinity up to negative 2, and it's also increasing from positive 2 to all the way up to infinity. The middle section, the roller coaster, and the function are going downhill. So therefore it is decreasing from negative 2 to positive 2. That's if you're given a graph. So here's another graph. Where is the function increasing and where is it decreasing? So it's increasing in the areas you're going uphill, and you can see it increasing from negative 1 up to 0 and also from 1 to infinity. And then where is the function decreasing? Well, it's decreasing in that region and that region. So we would say it's decreasing from negative infinity to negative 1 as well as from 0 to 1. Now, another typical word problem or problem that you might be asked to do is to find the critical numbers given a function and to also find the open intervals on which the function is increasing or decreasing. The first thing you'd want to do is you'd want to take the derivative. So we take the derivative, and we know that a function is increasing or decreasing when the first derivative equals 0. So we set the first derivative equal to 0 and factor and solve, and we get 2 points, x equals 0 and x equals 1. Put those on a number line like we've done many, many times in this class. Then we're going to plug values back into the derivative. So if I plug a negative 1 into the derivative, I would get 3 plus 3, which is positive. If I plug a 1/2 into the derivative, I would get 3 times 1/4 minus 1/2, I would get a negative. And if I plug 1 into the derivative, I would get 3. If I plug 2 into the derivative, I would get 12 minus 6, which is positive. Based on this, we know it's increasing from negative infinity to 0 and also from 1 to infinity, and it's decreasing from 0 to 1, which means 0, 0 is a max because it was going up and now it's going down. So that's the top of a hill. 1, comma, now I have to plug that back into the original function and I get negative 0.5. That would be a minimum because it was going down and now it's going up. So that's the type of analysis that you would need to do. Now we're ready to talk about concavity. Now for concavity, we're talking about, is a function concave up or is a function concave down? And you can see examples by what I mean for concave up and concave down. I generally try and picture my hand. If my hand is cupped and I can hold water, then it's concave up, and if it's cupped and the water's falling out, then it's concave down. The spot where it changes from being concave down to up or vice versa, we call those inflection points. From here then, we can move on into taking a look a little bit closer at this. Where the curve is concave down, look at what's happening to the tangent lines. The slopes started off very strong positive, very steep positive, and then they gradually got shallower and then they went negative. So the slopes of the tangent lines are decreasing. Since they're decreasing, that means the second derivative must be negative. So wherever a function is concave down, we have the second derivative being negative. Now, what's going to happen in the middle part where it's concave up? I'll let you think about that for just a second. Where a curve is concave up, look at what's happening to the tangent lines. They started off very steeply negative, and now they shallowed off, and then they went very steeply positive. So the slopes of the tangent line in this section are increasing. Since they're increasing, that means the second derivative must be positive. So the second derivative is negative, it's concave down. Where the second derivative is positive, it's concave up. And at the inflection points, the second derivative, if it exists, will be 0. Now, coming up on the next slide will be a nice little summary of all the different things that we've talked about. Now, keep in mind before that slide comes up that the second derivative can be 0 or does not exist. So summarizing, first derivative, if it's rising, first derivative is greater than 0. If it's falling, first derivative is less than 0. If it's concave down, second derivative, the red ones, are less than 0. If it's concave up, the second derivative is greater than 0. Inflection points occur where the concavity changes. So it changed from up to down, and that's where the second derivative would be 0 or doesn't exist. Maximums and minimums, that is at the top and at the bottom, and for those, the first derivatives would be either 0 or does not exist. All of these points are considered critical points. So when we start talking about critical points, we're talking about all of these points. So here's an example. We want to identify open intervals on which the function is concave up and where the function is concave down. So if we draw a picture, if I write on this, in this section, the function is concave down. So we would say it's down from negative infinity to 0. At 0, it changes, and now it's concave up. So up, we would say, is from 0 all the way up to positive infinity. Here's another example problem. So I give you a function, and I say find all the relative extremes. First thing I do is I would take the derivative. So I take the derivative, set it equal to 0. Then I'm going to factor out a negative 15x squared. I'm going to factor that some more. So I'm finding some critical points. So my critical points are x equals 0, 1, and negative 1. So I put these on a number line, negative 1, 0, and 1. And the next thing I'm going to do is I'm going to pick some numbers to plug into the derivative function. So if I plug in negative 2 into the derivative function, my value winds up being a negative answer. So I can put a little negative there in that region. Then I would plug in negative 0.5 into the derivative, and I would get a positive. Then I would plug positive 0.5 into the derivative, and I would get a positive, and then I would plug 2 into the derivative, and I would get a negative. Therefore, I know that negative 1 comma negative 2, and I got that value, negative 1 comma negative 2, by plugging negative 2 back into the original function, by plugging negative 1 back into the original function. Since at negative 1 it was going down, and now it's going up, I know it's a minimum. 1 comma 2 would be a maximum. I actually did that wrong. Negative 1 comma negative 2. It was going down, and now it's going up. So this one is a minimum. 1 comma 2 would be a maximum. Next up, I'm going to find the derivative, the second derivative. So I'm finding the second derivative off to the side, and I factored it, set it equal to 0, and factored it, and I got 0 and 1/2. these are critical points. So for critical points, I'm going to plug my values back into the second derivative. So if I plug -1 back into the blue equation up top, I get a negative answer. If I plug in 1/4 into the blue equation up top, I'm going to get a positive answer. And if I plug in 1 into the blue equation up top, I'm going to get a negative answer. So that tells me that 0, 0 is an inflection point because it changed from being concave down to being concave up. And 1/2, comma, now I got to take a minute and I got to plug 1/2 back into the original function to get the y value. So if I plug it into the original function and do some quick mental math, I get that the value for this is, drum roll please, can I do math in my head, 17/32, I believe. And that is also an inflection point because it changed from being concave up to being concave down. So these are the relative extremas. Now remember, 1, 2 is a maximum, not a minimum. So for a homework problem, I'd like for you to do this problem in the exact same way, finding the first derivative setting equal to 0, finding the second derivative setting it equal to 0, and putting them on a number line, and when you come in tomorrow, we'll be able to talk about them.
That's all, folks.
And before I leave you, this roller coaster I showed earlier was Coastosaurus from Legoland in Florida, and this is a picture of me and my son after are on that roller coaster.